Okay, so let's take a look at another way, another type of chemical reaction. So let's consider what happens when we increase the temperature of a chemical reaction. How does the rate of the reaction behave when we change the temperature? Well, back in Gen Chem 1, we talked about the energy aspects of chemical reactions. And when we're going to now expand that to include the energy associated with elementary steps. So the basic theory of what we're looking at is called collision theory. And this is, oh, I just spelled, if I can spell theory right, collision theory is the most up-to-date method of us looking at a chemical reaction. And so the text actually kind of gives us a generic template to use. Let's say you got molecule BC and you've got atom A. Well, if atom A comes in and collides with atom B, okay, what's going to happen is that we're going to eventually break that bond between atoms B and C, and it's going to form between A and B. But before that can happen, where you form the bond between atoms A and B, C goes off on its own, you have this transition where you start to form a bond between atoms A and B, and you start to break the bond between B and C. So we get to this point called a transition state. And so at the middle, there is a temporary unstable state, and we call that the transition state, in which where we're trying to form a bond. All right, so the bond forms between A and B, and then between B and C, the bond's breaking. Okay, and so this transition state occurs. This occurs as bond BC weakens and AB forms. Okay. Now there is an energy barrier to this because bond BC is pretty stable. So in other words, it's going to take energy to break that bond. So that barrier, we call that in chemistry the activation energy. A lot of times we shorthand this as E sub A, activation energy. And so if we were to look at a reaction in a little bit different way, we're going to draw something called a reaction coordinate diagram. And basically think of this as a way of us plotting a chemical reaction out. You've got the energies of the reactant, so potential energy is on the y-axis. The time or reaction progress is on the x-axis. And so for this reaction to occur, you have to gain energy until you get to this point where you get to the top of the hill, and then you start to release that energy. Okay, and we saw these back in Gen Chem 1, where if we looked at the level of the products versus the reactants, we said that this was an exothermic reaction if the products are lower than the reactants. If it's the opposite way, where the products are higher than the reactants, this is an endothermic reaction. Okay, so now we're looking at the reactants and where this transition state is. The transition state occurs at the top of the hill, because at the top of the hill, that's the energy barrier. That's the activation energy. So that's the amount of energy that you need to overcome that barrier. Okay, now there are some energy considerations shown here. So the change in energy, delta E, is exothermic for this reaction. How much energy is needed for the reaction to proceed? We need the activation energy, E sub A. Okay, now in a sample, some molecules are going to have enough energy and some won't. And this kind of comes back to something we've been hitting on back in back when we talked about liquids and solids. back when we talked about solutions, that depending on the temperature, you still need a minimum threshold in order to go from the liquid state into the gas state. And so the same thing applies here. We still, even at a temperature, you're still going to have a fraction of molecules that won't have that activation energy, will not have enough energy to get past that barrier. So looking at this graph, the fraction of molecules that have activation energy, E sub A, or more, will increase exponentially with increasing temperature. Okay. And so we can actually put what we're saying and take this picture and take the words, and we can actually put this into an equation. And that equation would look like this, where F, with a fraction of molecules with the right energy, is going to be equal to E raised to the negative E sub A over RT. Okay, where F, this is going to be the fraction of molecules with the right energy. Okay, is going to be equal to the F is that fraction of molecules with the right energy. E sub A, this is your activation energy. T, temperature. And an R, that's a universal gas constant. But since temperature is involved, we have to use the 8.314 joules per K mole value. Okay. So for a reaction, what variable can you change? What variable in this equation can you change to affect the rate? Temperature. Now this number, this fraction that you calculate out of this, is this going to be a large number or is this going to be small? It's going to be a small number. Remember, we're talking about a fraction, so we're definitely talking about something under 1. Okay. All right. Now, how would you characterize the sensitivity of the rate to temperature? So is it going to be very sensitive or will it not matter? Well, it turns out that raising the temperature, it does change the rate of the reaction. So this is very sensitive. If you increase the temperature, you're going to increase the number of molecules that have that fraction, that have that right energy. Now, in addition to temperature, or in addition to the energy, there is another factor that determines whether a collision will cause a reaction, and we call that steric factor. Okay, and we have a symbol, and it's like a lowercase p. Steric factor, what this is that this is the fraction of collisions with the proper orientation. So in order for a chemical reaction to occur, you've got to have molecules slam into each other with the right energy and the right orientation. Well, this first equation takes care of the energy part, but the steric factor takes care of the orientation part. All right, so the way that we do that. Okay, so one final factor before to consider, but it's really a primary one. At what rate do any collisions occur? Well, to calculate this, let's say if we take a normal rate law, rate would be equal to the rate constant K times the concentration of component A times the concentration of component B. We've seen this before. Now, to include the steric factor into this rate law, to make this work, the rate would be equal to the rate constant is made up of the steric factor P times the fraction of molecules that have the right energy times Z, the collision frequency constant. So this part right here, the P, which is the steric factor, times the fraction of molecules that have the proper energy, times Z, this all makes up the rate constant. Okay, and then this would be times the concentration of A times the concentration of B. Okay, now until you know the steric factor and you know the frequency, the collision frequency constant, and you know the fraction, you can't reduce this by the factors of the number that has the right amount of energy and the factor which represents the right orientation or the alignment. So that being said, okay, if we wanted to look at, if we wanted to give the equation for the collision rate, this would be equal to Z, the collision frequency constant, times the concentration of A, times the concentration of B. Okay, so Z, again, that's the collision frequency constant. Okay. Now, these two equations, okay, the rate constant, the two rate laws, what I'm going to do is set them equal to each other. In order to set them equal to each other, we see that the rate constant K was equal to the steric factor times the fraction times the collision frequency constant. So we're cool on that. Okay. But if I was to go back to the other equation that we got, the fraction equation here, and replace F with this, with E raised to the negative E sub A over RT, we would get something like this. K would be equal to P times Z times E raised to the negative E sub A over RT. Now, what I'm going to do is rearrange this a little bit so that way we can kind of get this a little bit in a nicer form. And what I'm going to do is kind of I'm going to skip a lot of steps ahead to get to an equation that says this, that K is equal to A raised to the E sub A raised to the negative E sub A over RT, where A is really the steric factor times the collision frequency constant. So these two really come together as your A. Okay, and so this is the A that we have in this equation here, and this is actually called, this equation that we just wrote down, this is called the Arrhenius equation.